has a countably infinite subset, and consequently A is infinite set means its size must be at least there is no infinite set which is smaller than a countably infinite set. So these are some of the simple things that we saw last time, and I will make a few more comments about these infinite sets. Rather passing, it may not be possible for me to go into, it will not be possible for me to go into all the details. It's also always a comfortable situation. Okay. Right, now what we want to start today is, let's start with any infinite set. Okay, so let me draw a picture. Start with any infinite set X. Then our property 3 says it has to have a countably infinite subset. So by 3, so 3 above implies X has a countably infinite subset. Say one of them is X1. So it has a countably infinite subset X1. So here is say X1. And the remaining portion we will call as X2. So let X2 be equal to X minus X1. That's X2. Okay, so clearly X1 and X2 are disjoint, and X union X2 is the whole set. So X1, X2 are disjoint, and their union is exactly X. Okay. Probably I should have, okay, doesn't matter. Should draw the picture there. Now we are going to focus on this X1. What do we know about X1? It is a countably infinite set, and therefore by property 2 it must be equivalent to a proper subset. Okay, so X1 being countably infinite, I will write CON from now on, countably infinite implies by property 2 there exists a subset X2 and it will be a proper subset. X2 with a subset of X1 not equal to X1, it is a proper subset of X1 such that X1 is equivalent to X2. So I should call it X2, I should call it X3 because I have used X2 here. So what is the picture now? I have X2, this was X1, inside X1 there is a X3, this whole thing is X1, and inside X1 is sitting an X3. X3 is a proper subset of X1. Okay, so I have split the set now into 3 parts. First I thought of splitting X1 and X2, then I split X1 itself into X3 and something extra, and extra is non-empty. Why? Because this is a proper subset. Okay, now what I am going to do is, I am going to define a map or a function from the set X to the following. Okay, so now let us define X hat to be X2 union X3. X hat is X2 union X3. Now I am going to take only this part and this part. So obviously it is a proper subset of X. So X3 is I am going to claim that x is equivalent to x hat. Okay, I will make x equivalent to x hat. Okay. So now what do I know? First of all, I know that x1 is equivalent to x3. So I must have a function from x1 to x3 which is 1 1 and on 2. Okay. Since x1 is equivalent to x3, there exists a function from x1 to x3 1 1 and on 2. So therefore, let me draw a big line here. From here to here is that f. Members of x1 are pulled to x3. And what happens? The entire x1 comes and sits inside the entire x3. It's 1 1 and on 2. So now define a function h from x to x hat as follows. Now when I say I want to define a function from x to x hat, what I want to do is, what does that function h do to each element in x? The result must be in x hat. It must take every element of x into x hat. So the elements of x are made up into two parts. Whenever an element is in this part, this f tells us what to do. And when it is in the other part, just don't do anything. Okay. So define as follows: h of x is equal to f of x if x belongs to x1 and x itself if x belongs to x2. So what we are doing is, any element here goes to the same element, and if some u is here, it goes to f of u. That's all. Now obviously this is 1 and on 2. Okay. The whole space is filled, the x2 part is filled, the x3 part has already been filled, so it's on 2. Since f is 1 1, there different fellows go to different things. Here its identity, obviously different fellows go to different things. So clearly h is 1 1 and on 2, and therefore x is equivalent to x hat. There is a 1 1 on 2 function from x to x hat, and therefore x is equivalent to x hat. But x hat is a proper subset of x, and therefore x is equivalent to proper subset of x. X is equivalent to a proper subset of x. We can therefore conclude, now 3 is not only true for countably infinite sets, now I can say any infinite set is equivalent to a proper subset of itself, and that is a characterization of infinite sets. Okay. So I will write here, therefore the today's first property is that any infinite set is equivalent to a proper subset of itself. So this is a characterization. Okay. What is a characterization? Being equivalent to one of its proper subsets is a characterization of infinite sets. Okay. So being equivalent to a proper subset of itself is a characterization of infinite sets. Now, what we have seen is that if we take any countably infinite set, we denoted its size by some symbol called LF0. The question is, when do I call a set countably infinite? Call a set a countably infinite set when it is equivalent to n. Now, the question is, are there infinite sets which are not equivalent to n? If there are, then I have to find another name. They are infinite but not equivalent to n. So, the question therefore is, are there infinite sets which are not equivalent to n? If so, it will lead to some gradation of infinities. Okay, who is bigger? If it is not equivalent, then it will be either equivalent to a subset of this, or this fellow will be equivalent to a subset of that. So, one of them will have to be bigger. So, what is happening? And we have already seen that there is no infinity less than LF0. So, if there is such a thing, it has to be more than LF0. So, in other words, we have two sizes of infinity itself. Now, we will investigate this question now. Okay. Are there infinite sets which are not equivalent to n? And we will see there are lots of them. There are many, many of them. So, how do we go about doing it? So, the first we introduce the notion of power set. Okay. So, I think I began this last time. So, let us consider a set A to start with, a finite set which has the elements A, B, C. So, A finite set. Okay. So, what is the size of A? With our notation, that will be 3. It is equivalent to the set to 3, and therefore, the size is 3. Now, what we are going to do is, let us look at all the subsets of A and make a set out of it. So, construct all the subsets of A and make a set consisting of all these. Consisting of all these subsets. I am going to look at it a little bit closely in two different ways, maybe some of the things in two different ways. What are the subsets? First, the empty set, and then the way I write will tell you what is happening. I am going to write next all the singleton subsets, then subsets which have two elements, and then the whole set is always a subset of itself. Now, I am going to make a set consisting of all these sets. The elements of the set are subsets of A, and this we denote by PA, and this is called the power set of A. So, in general, if A is any set, PA, the power set of A, is the set of all subsets of A. The set of all subsets of A. So, the elements themselves are sets. Which set? Subsets. Subsets of what? Subsets of A. Okay. Let us go back to this example. What is the size of PA, or the so called cardinality of PA? it has 8 elements now, it is again a finite set. I will write it as 2 cube. Okay, it is 0 element set 1 plus 1 element sets 3, 3C1 plus 3C2 plus 3C3, which is 1 plus 1 to the power of 3 binomial theorem. So, it is 2 to the power of 3. Okay. We see that the power set has 2 to the power of 3 elements, and in general we can now, from what I said, you can see that if you have a finite set with n elements, then the power set will have 2 to the power of n elements. So, in general, if the finite set having n elements, then the cardinality of it is 2 to the n. It will be 1 plus nc1 plus nc2 plus nc3 plus n choose 4, etc., n choose n, which is precisely 1 plus 1 to the power of n. Okay. Now, what is evident here is that the size of the power set in all these cases is bigger than the set we started with. If A had 2, PA had 4. If A had 3, PA had 8. So, PA looks much bigger than this. So, therefore, we see that for finite sets, the power set size is always greater than the size of the set. Okay. Now, what we are going to do is see that this is true even for infinite sets. We will show that even for infinite sets, the power set always has a bigger size. Okay. This is true even if A is. It's a peculiar argument, like the Russell's paradox in a sense. Okay. Probably I should have left that question, doesn't matter. How do we do that? Okay, so on the one hand we have A, on the other hand we have PA, the two sets. Okay. I am comparing now the size of these two sets, and the claim is that PA will always be bigger than A. Okay. First of all, we show that the size of A cannot be bigger than the size of PA. It has to be smaller. So, for any A, element A in A, we have the set subset consisting of only that element. Okay. So, we corresponding to every element in A, we have the corresponding singleton subset. So, where is this fellow lying? This fellow is sitting here because it is a subset of A, and this fellow is sitting here, is an element of A. So, now I am going to match the elements of A with the singleton subset. So, define a function, the function f mapping A to PA defined as FA is equal to the singleton set A. Okay. So, the point A is mapped to the subset A, which is an element there. Now, obviously this is a 1-1 map. If A is A1 and A2 are different, FA and FA1, FA2 are different. So, clearly F is 1-1. So, the moment you have a 1-1 map between these two sets, this cannot have size more than this. So, therefore, that implies the size of A has to be less than or equal to the size of P. What we are claiming is that equality cannot take place. We want to show that the power set is always bigger size. So, therefore, we want to remove the equality. So, we want to show equality cannot take place. Now, when will equality take place? They are equivalent sets. If they are equivalent sets, there must be a 1-1 onto map between them, right? And we will now show that there cannot be any onto map from here to here or here to here. Okay. Equality can take place if and only if there exists 1-1 onto map H, let us call it as G from PA, PM, right. They have to be equivalent, then there has to be a 1-1 onto map from one to the other. Okay, suppose this happens. We will show that that leads to a contradiction, and therefore this cannot happen. So, the contradiction is very funny, the way we get the contradiction is funny. So, suppose there is such a function. So, what does it mean? It means the following. I have PA, let me put it A to PA, whichever way, okay, this is easier. There must be a map with both directions, there must be a 1-1 onto map. So, there is A. There is PA and this G is going to go from there to there, and what it does is it converts every element to a subset. Okay. So, in other words, every person is converted to a team, some team as a member of some team. Okay. An individual becomes a team, the subset. The team may consist of only one fellow, does not matter. So, here are all teams. Here are all players. So, a player is going to be associated with a team, right. So, suppose this is onto, suppose this is 1-1 and onto. Then what it does is, it will take an A to a GA there. So, now let us see the picture separately here. A is here and the GA will be what? It will be an element or it will be a subset of A. So, it will be some patch in A, that is what GA is, right. Now, it may so happen GA may suck A inside or GA may leave A outside. So, therefore, what I am going to do is, I am going to look at the set, a set HG, it depends on G of course, all those elements of A which do not belong to the image patch. The picture should be like that. A must be lying outside its image inside the PA. Okay. So, A is taken to a team, every A is taken is associated with team, is not a member of the team. I am going to collect all those fellows who are not members of the team to which they are associated. Okay. Like I may be a supporter of Delhi Daredevils, but I am not a member of the Delhi Daredevils. So, I am going to collect all those fellows. Okay. Now, that fellow being collection of elements of A is himself a subset of A. So, that fellow is sitting here. This is one element. HG must be here, right. HG consists of all those fellows who are not members of the team to which they are allocated by G, right. Now, what happens? The map G is onto, and therefore, some G, H here must come and get mapped to HG. because G is on to every fellow as a pre-image. So, because G is on to, there exists an H in A such that G of H is Hg. Okay. So, there is an H here who must get mapped to Hg under G, and now that leads to a contradiction. See, now the question is, the two possibilities, H may belong to Hg, H may not belong to Hg. H may be outside Hg or H may be inside. Hg is a subset. So, this element A may be inside or the two possibilities outside the subset. Now, if this happens, that says H belongs to G of H. Hg is what? G of H. The moment somebody belongs to his image, you should not go to Hg. He is not qualified to go to Hg by very definition. It says H does not belong to Hg by definition of Hg. And that is a contradiction. If H belongs to Hg, H does not belong to Hg. It is simple like the Barber's paradox. Okay? So, this is a contradiction. And similarly here, H does not belong to Hg means H does not belong to Gh, but H does not belong to Gh is qualified to go to Hg. Again a contradiction. So, both of them lead to a contradiction, and therefore, there cannot be a one-one onto function, and therefore, we are done. Okay? So, therefore, there cannot be such a function. If there was such a function, it will lead to contradiction, and therefore, there exists no such G, and therefore, the PA is not equivalent to U. And we have already shown that the size of A is less than, and we have now shown it can be equal, and therefore, we have this important result that the size of A is less than the size of PA for every set A. Finite or infinite, it does not matter, always. In finite case, it was easy, we could count them. In infinite case, we have to go through all the matching processes. Okay? And when infinite sets came into being and Cantor did many of these things, there was a lot of commotion, and probably it was not accepted so easily. Okay. Now, let us see what are the consequences of such a thing. So, now we have seen that the power set is always more powerful than the set itself. Its size, its cardinal power is much more. Okay. Now, what happens? We have the set n, its cardinality is Aleph naught, which is infinity, but now by phi, the power set of n must be greater than Aleph naught, and therefore, it cannot be countably infinite. It is infinite, but it is not countably infinite. So, hence there are infinite sets that are uncountably. There are that are not equivalent to n. These are called uncountably infinite sets. So we will denote the cardinality of Pn to be Lf1, and certainly clearly Lf0 is less than Lf1 because the power set is bigger. Now we can write infinite number of papers. The power set of the power set will be bigger than the power set, and therefore the power set of the power set of n will have cardinality more than Lf1, and that we will call as Lf2, and so on and so forth. And P of n, P of n is a set. Take the set of all subsets of that, and that's a much bigger power set. That will be greater than the cardinality of n, Pn, which is Lf1, and we call this as Lf2. And then you can take power set of the power set of the power set of the power set. So we get Lf0 less than Lf1 less than Lf2 less than etc. So we get the infinity themselves are graded. This fellow is okay infinite, but there is some other bigger infinity sitting above him. There is some other bigger infinity sitting above him. So keeps on going. Okay, again there is like 1, 2, 3 ends up in an Lf0. These Lf0, Lf1, Lf2, that final infinity will be called an omega, and all this nonsense will go on and on. It becomes highly crazy. Okay, so we will not get into so many things. At least we now know there is certain amount of gradation of infinite sets. There is countably infinite and finite sets, countably infinite sets, uncountably infinite sets, and even among uncountably infinite sets there could be comparison of one being smaller or one being bigger. Okay. So there is it's not that all infinite things are same. Okay. One of the characterizations of the infinite sets is that it must be equivalent to one of its proper subsets. Okay. Now I do not intend getting too much into this cardinality. I am going to state a few things without any proof or anything like that. Okay. The first thing that I would state is the following. When we were small children, or if you look at the books that people start using at LKG, nowadays nobody went to school before first standard. Okay. I did not go to school up to 6th standard. Maybe that's why I'm a little poor in adding and subtracting. I don't know. Well, I was admitted to a school by my elder brother in the morning. I came back in the afternoon from school, lunchtime, and my father asked, "Why did you come back?" I said, "I know whatever they are teaching already, I know, I don't want to go." So next day my brother went and told them this is what he said. They said, "Okay, I will put him in 2nd standard." Then again I came back at lunchtime and said, "Whatever they are teaching, I already know, I don't want to go to school." So I just didn't go to school, and in those days you could get admitted in 6th standard by directly writing an exam. And so I wrote that exam and went into the 6th standard. But now in the 6th month itself, people start sending their children to school. Okay, whatever it is called. First it was called LKG, UKG. Then it is now called nursery. There is also pre-nursery. I don't know what it means. Okay. Anyway, so now if you take I just look at some of these books. Very nice in the sense that in the beginning we don't teach the child that 3 plus 2 is 5. They put 3 apples, another 2 apples, and another picture having 5 apples, 7 apples, 8 apples, and try to figure out where does that match, right? So they don't know 3 and 2 and 5, but they have a concrete realizations of this 3 and the 2 and the 5 in sets of apples. Okay, so they already in the idea that every set generates a cardinal number. Okay. and the set, a particular set is only a concrete realization of an abstract concept called a number. So now what we are saying is there are not even finite numbers, but there are certain infinite numbers like LF0, LF1 also, which can be realized through certain concrete sets, and every concrete set is the realization of some abstract number. And therefore, when we want to do arithmetic with it, we do just like children, because now as far as these crazy numbers are concerned, we are children. We have still not understood what they are. They are very abstract. So what we do is, whenever we want to add two abstract cardinal numbers, we first take their concrete realizations of two sets who represent that cardinality and see how through that set we can add. Okay. So therefore, some kind of crazy, simple arithmetic of cardinal numbers. When I say cardinal number, every set is a cardinal number for me. It generates a number, and all sets are equivalent to that are the same number realizations. Okay. Now, first of all, therefore, we will look at the arithmetic that we know. The arithmetic we know is of arithmetic of our ordinary finite numbers, 1, 2, 3, 4, 5, etc. So we see that arithmetic and we go back to our nursery days and see how it was interpreted, and that interpretation again we will use to get the arithmetic of these things. Okay. So now, first of all, addition. So in other words, if I have two sets, I have their cardinality. How do I add those two cardinalities and get another cardinality, and what is the set that realizes that cardinality? These are things that we have to look at. Okay. Now in finite case, I have number 2 and number 3. How do I add them? If I now take a set which represents the number 2 and a set which represents the number 3, then what does represent that number 5 which you have in addition? The x union y represents the number 2 plus 3. But however, if it was like this, x union y does not. So if x is the realization of the number 2 and y is the realization of the number 3 and they are disjoint realizations, then x union y is the realization of the number 2 plus 3. Now we use the same thing. If x is a realization of a cardinality and y is a realization of a cardinality and x and y are disjoint, then x union y is the realization of the cardinality x plus y. Is that clear? Is there something funny there? Think about it. If x is a realization of a cardinality, y is a realization of a cardinality, and x and y are disjoint, then x union y is the realization of the cardinality of x plus cardinality of y. Is there some problem with that definition? Think about it. Things may come out like this. What is the guarantee that I will get two disjoint realizations? One realization for x and one realization for y, such that they are disjoint. Okay, but that's always possible. Just think about it for a moment. We know what it is. So with that in mind, we say x y disjoint, then the cardinality of x cardinality of y is defined to be the cardinality of x union y. So that's a quick way of defining. Now this product is a difficult thing. How do I define the product? So I have to go back to the usual common numbers that I am used to and see what is the product and how I can interpret the result in terms of sets, so that once I have the result in terms of sets, I can copy it here. So let us say 2 into 3 is 6. How do I realize it in terms of set here? 2 can be realized as AB, 3 can be realized as set XYZ, but how can I realize this number 6 from these two? The Cartesian product x cross y will have exactly 6 elements, and that's what we are going to use. The Cartesian product of x and y is, by definition, that size is called the product of the two numbers, the x and the cardinality of x and the cardinality of y. Now I'll just give you one more thing. How do I define 2 to the power of 3? See, 2 to the power of 3, I know it's 8. How do I now bring it to this level? I can't say it is 2 into 2 into 2. Then if I want to do it, I say x cross y cross z. Then there are more of them. How do I do? There are infinite of them. How do I handle and things like that? So, what is meant by infinite number of Cartesian products? That's exactly what we are trying to do. So now I have to find some way of 2 to the power of 3, which is equal to 8. Some of you have done a simple combinatorial course with Madhavan or somebody on first day, probably would have given you an exercise. If I have a set with n elements, another set with m elements, how many functions can I define from this set to that set? Let's say, suppose I have a set with x with n elements and I set y with m elements. How many possible functions are there from x to y? Huh? For this fellow, there are m choices. For this fellow, there are m choices. So it is m power n. Okay? So now that suggests, if I have a cardinality, let me call this as m and this as n, so that my notations become all right. Then if I want a cardinality mod x to the power of mod y, how should I define? This should come out of the domain set. Take the set x, take the set y, and look at all possible functions from x to y. So, I am going to define mod x to the power of mod y to be, look at all functions from y to x and look at the size of that. That's how mod x to the power of mod y is defined. Okay. The cardinality mod x to the cardinality mod y is the set of all functions from x to y. So let's look at one simple example of that last thing. Or second, okay, even I'll look at a simple thing about the second. What is LF naught times LF naught? What is LF naught times LF naught? It is n the cardinality of n cross n. The n cross n is n squared. We saw that n to the k has the same cardinality as n, so it is again Aleph naught. So Aleph naught into Aleph naught is Aleph naught. Very crazy. That doesn't mean Aleph naught equal to 1. You cancel Aleph naught on both sides and write Aleph naught equal to 1. So these cancellation laws are very dangerous. Okay, here you don't cancel things like this. So the first thing that we see is that by 2 Aleph naught into Aleph naught is the cardinality of n cross n, which is equal to Aleph naught. Okay. Let me look at an example of 3 to start with. So what is 2 to the Aleph naught? So now we are in this situation. I should for x take a set consisting of 2 elements, and for y I should take a set which is countably infinite. Okay. So I can take x as so what is y? I should take y to be as y to be equal to n. Okay, it should go from y equal to n, and for x I should take 2 elements, so I will take 0, 1. Okay. So now I should look at all functions from n to 0. What does that suggest? What is meant by a function from n to 0, 1? All are living in modern days. It's simply a binary string, infinite sequence of zeros and ones. So when you have infinite sequence of zeros and ones, what does that suggest? Huh? I'm not talking about power set. Anything that you know is always representable by an infinite string of zeros and ones. What do you represent in binary strings? Say point A1, A2, A3, A4, A5, A6, A7, etc., where all the A's are zeros and ones. What will it give eventually? A number. What number? Real number. Which real number? If I write something like this, what do you think it will give? It will give between 0 and 1. Okay. This suggests, I want you to complete this. This suggests that there is some connection between 2 to this 2 to the power of Aleph naught, these functions, and the real numbers between 0 and 1. In fact, they are exactly the same size. Okay. But the real numbers between 0 and 1 are the same size as the real number r. Okay. So the 2 to the r are the same size as 2 to the power of f naught. That's one of the Cantor's arguments. Okay. I want you to really technically write this proof because you are all great 0-1 people. Everybody does only computers these days. So the 0-1 people should be, there may be minor technical problems here, but handle it carefully. But eventually you will therefore find 2 to the power of Aleph naught is the same as the cardinality of all the real numbers, which is the same as the cardinality of R, which we are going to denote by okay. That's a new terminology instead of Aleph. There is in honor of, because Cantor wanted to screw up people and put his name there. Okay. See, this is very technical. See, when Banach introduced Banach space, he called it B space, and he knew that definitely someday people are going to call it Banach space. Okay. Hilbert didn't call it as H space, but maybe he did. I don't know. So now what have we got? We have got this string of this was the 2 to the lf naught, okay, and this is the same as the size of the real numbers. The question is there a set whose size is, it is uncountable, so it is more than this, but it is not as big as the real numbers. It is not as big as 2 to the power of f naught. So a basic question that Cantor raised was is there a set x such that it is uncountably infinite, lf naught is strictly less than mod x, but it is not as big as 2 to the lf. And the answer is yes and no. The standard axioms of the set theory, yes is also a consistent answer, no is also a consistent answer. It is an independent axiom. Okay. It was proved in the middle of the 20th century by Cohen that this is an independent thing from the other axioms of set theory. Okay. The Zermelo-Frankel axioms of set theory. Will not get into observation. So Cantor said that is called the continuum hypothesis. What is the spelling of continuum hypothesis? This is called Cantor's continuum hypothesis. The answer is no. That is, there is no infinity between the integers and the real numbers. The next level of infinity after the integers is the real number infinity. There is nothing in between. So, okay, this hypothesis is independent hypothesis. Okay, independent axiom in set theory. So this is shown by Cohen. I don't know, somewhere around 1950s. You know, in the middle of the 20th century, there were two such great results. One was Gödel's incompleteness theorem, and immediately together with him was Cohen's independence of the continuum hypothesis thesis. Okay, so these were some earth-shaking results. These were earth-shaking results because they destroyed Hilbert's dream that everything can be axiomatized. Okay, and people coming from the same school started showing that no matter how consistent your axioms are, there are always results outside your system. Okay, so they, in more or less, the grand program of Hilbert to axiomatize everything died in a sense. Okay, so I want to make one or two comments. I mean, these are all some random comments which we will be using at some part of the course. So therefore, it's better I put it somewhere. So what did we have? So here are some of the results that we have. 6, 7 is 2 to the lf naught is equal to c, and then we had the continuum hypothesis. Okay. Now I want to look at a few things. First of all, let us look at a set A and its power set PA. This has cardinality A, this has cardinality P to the A. What is the connection between these two cardinalities? Okay. So what I am going to do now is, what does this mean? What does this 2 to the power mod A mean? This is the size of all functions from A to 2 is 0, 1 set. The set having 2 elements and the cardinality of that. That is what this means. 2 to the mod A means the collection of, you take the collection of all functions from A to 0, 1, and that is a huge collection of functions, and look at the size of that collection. That is what 2 to the power of mod A by definition of our mod x to the power of mod y, right. Now take any such function in this. Okay. Take any such function. What does it do? How does it look? Here is A, here is just 2 point set 0 and 1. It will take an element, put it here or put it there. So f can take x to each element x to either 0 or to 1. So now what I do is I take the following set, all those elements in A, okay, let me put A, all those elements in A for which fa is equal to 1. That is those points where it does not vanish. At other point it vanishes, and this is called the support of f. So I am going to look at, take any member of this collection, starting from the member of that collection I have constructed a set. The set is all those points of A at which f takes the value 1. Now this SF is a subset of A because it contains certain elements of A. So therefore SF belongs to, is an element of the power set A. The elements of the power set A are subsets of A. So what have I done? So I have taken the set F A to 0, 1, and from that I am now looking at PA. I have started with an F and now I have associated that with an SF there. Is that clear? With every function I have associated a subset of A. So now I have a mapping from this to this. Call that mapping as H, whatever it is, phi. So let phi mapping F A 0, 1 to PA be defined as phi of F is the support of F. Phi of F is the support of F, then phi takes a function to a set in A. And therefore, now clearly 2 different functions will have 2 different supports, because they have to differ at least at one point. So at one point where that fellow takes 0, this fellow must take 1 or vice versa. Okay. So clearly f not equal to g implies sf not equal to s. G implies phi f is not equal to phi g. So therefore phi is 1, 1. Okay, therefore phi is 1, 1. So if we have a mapping from here to here which is 1, 1, the size of this must be less than or equal to the size of that. Whenever you have 1, 1 map from here to here, that fellow has at least as many fellows as here. Size is this. Okay, that is the first thing that we got. Now we look at the other way around. We looked at a function and constructed a set. Now we look at a set and construct a function. Okay, so let A K belongs to PA. What does that mean? Here is A and K is a subset of PA. Now construct a function for whom this is the support. So let F map A to 0, 1 be defined as f of x is equal to 1 if x belongs to K, 0 if x does not belong to K. So what happens? We have now constructed a map psi from PA to F A to 101 defined as psi of K. I will call this function as Fk, which belongs to that. Okay. Now what can you say about this psi? Different sets will now go to different functions. So K1 not equal to K2 implies Fk1 not equal to Fk2, therefore psi is 1, 1, and therefore the size of PA must be less than or equal to the size of F. So we have got the two inequalities, and now Schroeder-Bernstein's theorem says when both of them A, the cardinality is less than or equal to that, and that cardinality is less than or equal to this, there must be isomorphic. So therefore I'll write it SBT. Schroeder-Bernstein theorem says this is the same as this, which is what we call as 2 to the minus. Yes. Let K belong to a subset. This is a subset of K belongs to PA. That means it is a subset of A. Now I am going to define a function from A to PA. I'm sorry, what should it be? I am going to define a function now from A to 0, 1. How do I define that function? Whenever the point is in K, it is 1, the light is on. Whenever a point is outside, the light is off, it's 0. Okay. Now this is clearly a function from A to 0, 1, and this is the collection of all the functions from A to 0, 1. So F belongs to that side. So this psi which connects this set K to Fk is a function from PA to F A to 0, 1. Okay, and that is 1, 1, and we got it. So what we say is, what we normally intuitively do is correct. The cardinality of PA is 2 to the power of the cardinality of A. The cardinality of the power set is 2 to the cardinality of the set itself, and that's what we got, right, in the finite set. The cardinality of A is 3, it was 2 to the power of 3. It was 4, it was 2 to the power of 4. Now that notation is true even in the infinite cases. The cardinality of the set of all subsets of any given set is 2 to the power of A. And therefore, what does that say? 2 to the power of LF naught must be the set of all subsets of N. The cardinality of this power set of N. This should be this is the cardinality of N. So this should be the cardinality of the power set of N, and this is the cardinality of the real number. So it is the real numbers equivalent to the set of all subsets of N, which follows from Cauchy's construction of real numbers through equivalence classes and so on and so forth. Okay. We will not get into all those details. Thinking about real numbers, you will get that idea. Okay. So now we have got some. Well, probably I started something last time, which or the previous time. I should complete that now. Okay. Now here are some questions. What is the cardinality of R squared? That's a tricky question, right? What is the cardinality of the plane? Now, first of all, R is interval 0, 1. R is equivalent to this interval 0, 1. So, we had last time the Cartesian product will be equivalent to 0, 1 cross 0, 1. If x is equivalent to x1, y is equivalent to y1, we said x cross y is equivalent to x1 cross y1, which you observed last time. So, therefore, what we have to look at is only the unit square. Okay. Now, what is the cardinality of the unit square? The claim is it is the same as the cardinality of the unit square, the line. Now, very dangerous things are happening here. Okay. What we are doing here is, again, these are all questions. Okay. You have to fill in the blanks or look at some books. If you look at either Hewitt and Stromberg or somewhere, you will find maybe a one line mention somewhere here or an exercise there and so on and so forth about these things. Okay. What this says is, if you take the unit square and if you take only this, there are lots of things that are happening. If you are viewing these two fellows from the point of view of area, the interval as area, what? 0, height is 0. So, the interval as area or measure 0, whereas the square as area 1, assuming the standard measure. Okay. So, therefore, there is a world of difference between interval, the unit square, from the, if you are looking at it from the point of view of measures. But if you are looking at it from the point of view of simply points and sets, they are both same. Nobody is bigger than the other. Each is equal. So, therefore, again, the small big is a matter of perception. What is the specs that you are wearing? Based on that, you will see as something as very probably, for an ant, we are like monsters. Okay, that we look too big for it. But then, for a monster, whether an ant or you, we will crush both of them with one leg. Okay, so both of you are same. So this who is looking at what in what context? Okay, so therefore one must be very, very careful. So we will see now. We already seen that the same two things may look totally different from the point of a measure theory or area wise, and same from the point of set theory. We will now subsequently introduce the notions of some of the ideas of topology, and there we will see there the notion of something being very small topologically and very big topologically is different from these two fellows. So therefore one must be extremely careful when somebody just dismisses something as small. Small in what sense? Okay. So you must be very careful in the set theoretic connotation, whether you have a unit line or a unit square or a unit cube, they are all of the same size. That is very strange. Okay. Oh, but from dimension analysis point of view, you may say that is dimension 1, this is dimension 2, that is dimension 3, but I don't care for dimension. Finally, they all have the same number of points. Okay. So therefore, these notions of big and small that we are discussing are of the same, being the same size, is purely, these are all the set theoretic ideas. Okay, set theoretic size connotations. They will be different in some other context. Okay. Any questions on this? It will take a while to get used to these things, but best thing is sit down and write down these things yourself. Then when you put it in your language, you realize, oh, this is not clear, that how do I put this, how do I connect these two, and you will then see. For example, even to realize that this definition, how do you get it, you have to see how it comes for normal numbers, and then from that you go to this. So now figure out a few of these ideas, and some of these arithmetics are very crazy, okay, but let's not get into too much of these discussions. Right. So now I am going to look at a few properties of countably infinite sets. Let me at least begin, state some of these things. We will probably very quickly prove them next time and move on. Okay. Even before that, let's use a terminology. We have finite sets, countably infinite sets, uncountably infinite sets. And the smallest level of infinity is the aleph naught, countably infinite. Anything beyond that, I am uncomfortable. Things are getting out of control. So most of the time, we will somehow be dealing with sequences or finite things. Okay, whatever we do, we will try to be within that thing. So any set which is either finite. When I say finite, I include the empty set also. The empty set is having 0 elements. Finite or countably infinite is called a countable set. I will include both of them in this terminology. It's called a countable. So when I say countable, I mean either finite or countably infinite. Okay. So now let's look at some very simple properties. Suppose I take two sets A and B, both are finite. What can I say about A union B? That will also be fine. So there is no problem. Okay. Suppose I take a finite number of finite sets, then what can I say about the union? Yes, it again will be finite. Now suppose I have a countably infinite number of finite sets. Countably infinite means it can be arranged in a sequence. So I have a sequence of finite sets. What can I say about the union? Countably infinite? It can be either finite or countably infinite, because some of them may be simply repeating. I never said they are disjoint. Simply A1 may be equal to A2 equal to A3 equal to A4. All of them may be the same set. So, or it may be this fellow has something, this fellow has something different, this fellow has something different, this fellow has something different, then all of them will add up to a countably infinite set. So, this is either finite or I can simply say it's countable. And countably infinite if they are disjoint, for example. If they are disjoint, they are definitely countably infinite. Each fellow will come give at least one element, and therefore it will become countably infinite. So therefore, if I know when I put together finite number of sets, finite sets, I know what happens. Now I want to look at what happens when I put together countably infinite sets. Okay. So now I am going to look at countably infinite sets. Suppose A, B countably infinite. What can I say about A union B? Can it be finite? already both of them are countably infinite. That has to be countably infinite. Okay. Now suppose I have countably infinite, finite number of them. What about the union? Again countably infinite. Now what about a countably infinite union of countably infinite sets? Countably infinite union of countably infinite sets. Huh? Will it be countably infinite? What's your guess? Either countably infinite or uncountably infinite. That's no answer at all. It's a set, you should have said. The question is, will it be countably infinite? Now it will trespass and go into the other side. Okay, will this be? Countably. Now this is another great proof of Cantor. I mean, various ways of looking at it. Cantor, I think he drove people crazy with all these proofs like this. Okay? And it turns out it is countably infinite. So that's the advantage of these countable sets. So what you can put all of them together, you can say countable union of countable sets is at most countable. Countable union of countable sets is countable. You put finite, countable infinite, all these things, anything together, you will always be within that realm of countability. Try to give a proof of this. Okay, intuitively, how do you proceed with such proofs? Okay. Now let me tell you how a general proof like this should be written, probably, and looked at. Now, in all these cases, without loss of generality, this is a typical mathematical statement, which means there are several small things which I want to write, which I am lazy to write. You can take care of it, and therefore I say without loss of generality. I don't know the WLG who invented. Without loss of generality, you take all the sets to be disjoint. Okay. Even in the disjoint case itself, it's going to be countably infinite. In the non-disjoint case, is automatically going to be countably infinite. So they are all infinite union of disjoint, mutually disjoint. So just look at that case, mutually disjoint, countably infinite sets. So what does that mean? First of all, I have an indexing set for these fellows. So I have a set I, and I have for each I in I a set AI, such that LF naught and AI intersection AJ is empty. And this index set is also countably infinite. So that's what is countably infinite union. So the indexing set is countably infinite. The sets involved are countably infinite. They are all disjoint. Okay, so what you have to do is, I have a set I such that there is a mapping from n to I. which is 1 1 on 2. Okay. Why is that? Because I is countably infinite, there is indexing set. Then there is a mapping from I to this collection of a collection K of disjoint sets, and which is also 1 1 and on 2. For every point in the index set there is a set there, and that set any two of them must be disjoint. So now the question is union I belonging to I, AI is equal to Aleph naught. Prove. That's what the question is. What does that mean? That means call A or the union of I belonging to I of AI. Okay, you want to show that mod A is equal to Aleph. This is the problem that we are trying to show, but the union is Aleph naught. You already know why. Why we already know that? Because take for instance any one of the i's, AI, it is equivalent to a subset of A, namely AI itself, and therefore the size of AI must be smaller than the size of A, but the size of AI is Aleph naught. So Aleph naught is already less than or equal to. So the only thing to show is, only thing to be shown is mod A is less than or equal. How do we show that? Suppose we can construct. Okay, I think I will leave it at this. I will leave it to you to prove that. See whether you can show that mod A is less than or equal to Aleph naught. If not, I will give you the proof next time. So what we have therefore is, what will happen if I put a finite set and an countably infinite set and take the union? If I take a finite set and a countably infinite set and take their union, that will still be countably infinite. So therefore, when I mix this finite or countably infinite, I am not going to go beyond the realm of these things. So therefore, countable union of countable sets is countable. That's what the word countable means. I may be having finite or I may be having countably infinite. So countable union of countable sets is countable. That is the one important observation of Cantor. So we will be using these facts very, very strongly. Okay. Now what I will do in the next class probably is very quickly dispose of the last section of my preliminaries. I will quickly introduce you to Zorn's lemma, which we will be using several times in the course in functional analysis, and then I will very quickly go through some standard inequalities, which again we will be using ad nauseam in our course. So that will be the last lecture of preliminaries. Okay. Next time I will do the Zorn's lemma and inequalities, and then we will be ready to start with the chapter on metric spaces. If we understand metric spaces well, we can zoom through the rest of it, because there will be others with additional properties which will only help us do better and not hurt us more. Okay. So subsequently I will do the chapter on metric spaces. Here I will bring in many of the standard properties of metric spaces and then go to the other aspects of functional analysis. I think when you come to a class, you must stay till the end of the class. You can't walk out in the middle. This is not a cinema theater. Okay? If you don't want to come to the class, don't come. I have not asked you to come, you have volunteered to come. I don't like my attention being disturbed by this sort of movement. Okay. Right. Okay. Okay, so we'll meet Friday 3:30.